Hello everybody. From this section, we're going to talk about integrals of multivariable functions. At the beginning of this course, we started computing limit of multivariable function, for example, a function of two variables. When xy goes to some target point. And then based on this calculation, we can develop partial derivatives. So suppose you have two variable function, we can compute x derivatives and y derivatives and so on. We can of course talk about higher derivatives, higher order derivatives. Now the next thing is integral. So derivative then integral. So for multivariable function f, suppose it has two variables, then usually it gives this kind of form for its integral. It's called double integrals. And easiest way to start with is rectangular domain. Alright, this part is from 15.1, section 15.1, and we're going to use Fubini's theorem to find double integrals over rectangular domain. Alright, so what is double integral? And one easy answer is volume interpretation. So our topic or our integral is written in this form, and it's called integral of f of xy over the domain R. A stands for area, so this is an integral of f over domain R. And what is R in the picture? R is the bottom of this 3D object. We can think of this is a tent in your camping site when you go to camping site, and f of xy, usually we say this is a surface or mountain surface. Now we can think of this as the top of your tent. So the integral of f over R is a number which indicate how big is your tent is. So in other words, it's the volume of your tent covered by f of xy. And the way to calculate this, the very original idea is to approximate it by rectangular boxes. So you fill up your tent with a lot of rectangular shaped wooden blocks, and then for each block, because those are rectangular shape, each block we can easily find its volume, and then take the sum of all the blocks. Then we have approximation of this volume. So there's three pictures telling us how to compute this volume under a tent, in your tent. So firstly, we use 16 blocks to estimate the tent, the volume, and then we can use n equals 64, which gives more accurate volume. And now if we use even more blocks, 256, then it could be almost precise. But the theory says when n goes to infinity, that's exactly what you're looking for. This is exact value of the volume. So that's why we put limit here, and it's called, this idea is called Riemann sum. All right, to calculate these, so these we have to talk about Fubini's theorem. So first, let's see what we mean by Fubini's theorem. So if we read it, so f of xy, this is a given surface, or the top of your tent, which is continuous. It's a nice thing, continuous. throughout the rectangular domain R. So R is given by X range and Y range. So we can think of, suppose A is here, B is here, C is here, D is here. No, D is bigger than C. So then the rectangular domain is like this. And we can think of this is the bottom of your tent, and we have a top of your surface of your top of your tent, and we're looking for its volume. Then what we do is we are planting woods or fill up your tent with some blocks. So basically we can think of partitioning your tent with a lot of blocks, and for each one we can find certain volume. So we have a number here, a number here, a number here. The number stands for the volume of each wooden blocks which was standing on each small rectangle, and then take the sum. That's what you do. That's Riemann sum. Now, how do you take the sum? Of course, we can randomly hop from one rectangle to the other rectangle, and then at the end we search everything and take the sum. But this is not the way we do that. The Frobenius theorem actually tells you two ways to collect all those numbers placed in each small rectangle. So when we collect, this one tells you one way you can collect those numbers. We can think of those are just coins placed on each box, and you won't collect all the coins together and put it into your pocket. But there are two ways by Frobenius theorem. First, so dx, then dy. In dx means running in x, running variables x. So you are running along x-axis. What it means is we fixed y, and we can run along x-axis and x-axis, x-axis, and then once you got to the end, then we shift to another x-axis. So when you run x, y is constant, y is fixed. So run, and then run, so all the way to the top. This is the way we interpret the first one. Another way you can collect all the coins placed on each box is you first run in y direction, and then gradually you shift to another x direction, so from A to B. Excuse me. So Frobenius theorem tells us you can either collect horizontally, or here you can collect vertically. And in any case, as long as you've done your searching process, then you end up with the same number, which is double integral. All right, let's use that theorem to this example. So we are going to evaluate double integral when f is given by this, and R, the domain, is given by this. So first we look at what R stands for. So R is x is changing from 0 to 2, so 0 to 2, and y is changing from -1 to 1, so -1 to 1. Then the rectangle domain R is given by this, and we can think of a surface or a tent planted on this bottom. The surface is given by here. Now we first look at dy dx, so running in y direction, and then we shift gradually in x direction. So we're going to, so for example, we can collect along this line, and then this line, this line, this line, so all the way to the end. So we write the surface first, and then dy dx, but y is running how much from lower limit -1 to upper limit 1, so from -1 to 1. And then next we run x, which means 0 to 2, 0 to 2. Now when we evaluate or compute this actual value, we first start from inner side. So 0 to dx is outer integral. The inner integral is along y direction. So you are running along y direction. In other words, vertical lines. So what we do is, at this case, we freeze x. X is fixed. So freeze x. Just like x is a constant and y is changing variable. So to compute this integral, 100 antiderivative is 100 y, not x, because y is changing variable, minus now 6x squared. Those are frozen, it's a constant. Y is the only variable, so 6x squared, its antiderivative y is 1/2 y squared. And then we plug in the upper and lower limit for this inner integral. Then we get 200, because 1, if you put it in, this is 100. -1, you put it in, then -100. So 100 minus -100, which is 200. Now, minus sign comes from here. And this part is 3x squared y squared. So 3x squared y squared. Y squared has to be plugged in with 1 and -1. And if you look at here, this is 3x squared, y is replaced 1, and then -1. And this becomes 0, so 0 to 200 dx, and antiderivative with respect to x, and 0 to, which is 400. Another way to evaluate this integral is by suggested. So Frobenius theorem says it doesn't matter which order you go. So you can go y direction first, or you can go x direction first. So let's look at second one. So when I do 100 minus 6x squared y, if I go dx dy, then for dx it's changing from 0 to 2, and for dy it's changing from -1 to 1. And that gives different computation, but at the end we should have the same number, 400. So again, we don't touch the outer integral, the inner integral. Antiderivative is 100x minus 6y. Y is frozen now. This is frozen. So 6y. X squared is variable, so this is 1/3 x cubed and 0 to 2. So if you calculate for 100x, when you put 2 and 0 and take the difference, it is 200. And this second term is 2yx cubed. And y is not changing, y is just frozen. Just think of a constant. So the whole thing here is 2y and x cubed, so 2y. And x cubed will be replaced by 2 and 0, and then take the difference. What it means is 2 cubed minus 0 cubed dy, which gives me 8. So negative 1 to 1, 200 minus 16y dy, and antiderivative of this, it goes to single variable calculus, so 8y squared and negative 1 to 1, so 400 first, and then 8 times 1 squared minus negative 1 squared, which is 0. So the answer is 400, which is consistent to the other direction computation. All right, there is a small code which is using the command from the MATLAB. So we use fserv to define the function and the bottom, so that the domain, and integral gives you integration. All right. Find the volume of region bounded above by elliptic paraboloid, which is given by this. So this is your tent, the top of your tent, which is given by this, and find the volume under this, which means you need to take a double integral, and this bottom region or domain is R, given by rectangular domain. So if this picture, 3D picture, is not clear, then we can just draw a picture for the domain, which is xy axis, and x is 0 to 1 and y is 2, so something like this. And we can think of they're coins you want to collect, but it's up to you. You can either collect horizontally, then that means dx dy, or vertically, then dy goes first, then outside is dx. All right, let's just pick randomly. So 10 plus x squared plus 3y squared, and I'm going to do dx dy. So we are running horizontally and then gradually shift to in direction y. Then if you choose x as inner integral, then we look at x range, which is running from 0 to 1, and y is outer integral, which is 0 to 2, specified by the problem. And then as usual, we do the inner integral. In that case, y is frozen, just constant. So here 10, its antiderivative is 10x, right? And x squared, it's the antiderivative, and 3y squared, which should be thought of a constant. So a constant antiderivative is the constant itself multiplied by y, multiplied by running variable x. So 3y squared x 0 1, and then dy. So if you calculate, this is, here's 10 plus 1/3 plus 3y squared dy, and antiderivative 10 1/3 331, antiderivative is y, and 3y squared antiderivative y cubed 0 2. and that gives me 31 over 3 times 2 plus 8, which is 362 plus 24 and 86. Okay, I think that's pretty much everything for this section, and we are going to stop here.